which basically uh, puts all the maths we had done in a slightly neater form than what happens when I write it about. I just wanted to show you some simulations I did and show you some field distributions we get. But this file has been uploaded, and basically it is putting things in a nicer form. So all the calculations we did, these are again everything we did before. All these calculations have been put in a nice form. How the solutions come about have been put in a nicer form. So you can, if you have trouble looking at the handwritten slides, I hope these slides would help you in getting to the answer. Before we talk about other parameters we want to finish about in the rectangular waveguide, what I wanted to talk first was about some simulations I did to show you how the electromagnetic field distributions look like in these waveguides. So the goal for today would be, yesterday we had seen this, we had drawn the cuts, but it's always easier to see three-dimensional pictures and understand what's happening. So I'll show you some modes, some important modes which can happen, and color plots for that. And then we'll talk about other properties which we want to understand, including the group velocity, the phase velocity, group velocity, wave impedances, and finally the attenuation. What kind of attenuation do we get in these rectangular waveguides for different modes? With that, today I expect to finish your unit 4, the rectangular waveguides. And then from tomorrow onwards, we will, tomorrow we can probably do some questions on rectangular waveguides. And then from Friday onwards, we'll go to cylindrical waveguides. So before we do cylindrical waveguides, I'll have to teach you new maths. So we'll spend some time learning about something called Bessel functions. So yesterday we had talked about what the electromagnetic field distributions are looking like. These solutions which I have are finite element method. So basically, you take the waveguide and you break it into a grid, and then you solve Maxwell's equation at every single point in the grid, and you look for how the propagation is happening. So this is basically, if you look at the top one over here, this is instantaneous E field magnitude, which you're going to see. And if you look at the bottom over here, that's instantaneous H field magnitude. Again, remember this is the kind of feature we were seeing, that if I was looking at TE10 mode, in the X direction, so you have the X direction this way and Y direction upwards. In the X direction, you have a sinusoid variation. So you basically have, one tells you that there is one lobe in the X direction, and in the Y direction, 0 says there is no lobe, so it should be constant. So in the Y direction, things are constant. If I plot this electric field, you basically see that kind of behavior. Here, red means a hot spot, means the intensity is larger. Green is where the intensity is 0. These are just the numbers of the electric field, some arbitrary values. I just gave some arbitrary power into the waveguide. So again, what you notice is that same kind of cross-sectional behavior we had seen. If we go in X direction over here, you see that there is an intensity variation which happens, and if I took this cut, if I just took a cut across this here, the intensity variation would be of the form of a sinusoid. But if I go in the vertical direction on the top and the bottom, there is no uh, on the vertical direction there is no uh, there is no uh, variation. So that's why you don't see any color gradation which happens in the vertical direction. So it's telling you, this chart is telling you that in the vertical direction the field is remaining constant. In the horizontal direction, the field intensity is changing. Similarly, you can plot the edge field magnitude, not the phase, but just the magnitude part here. And again, you see that the edge field uh, uh, is pointing in a different direction, so the field vector is different. But again, it does not vary in y direction, as you can see with the cuts we had talked about yesterday, but it does vary in the same form in x direction. So you see that the edge field variation, this is now an hy field, whereas the top one is an ex field. There is an hy field, and that variation is basically given like that. And then this field is propagating forward as a wave, and you can clearly see the waveforms which are created on the top in x and y direction. So this is what the TE10 mode would look like inside the waveguide. If I went inside the waveguide and I actually measured the power, it would basically, the power distribution would look like effectively that color gradation which I am getting over there, red being higher power, green being low power. Again, remember the power would be E cross H, the power density would be E cross H, and E and H have the same sinusoid variation in the transverse plane. So effectively, this is how the spot of this waveguide would look like as electromagnetic energy is traveling forward. If we go to the TE01 mode, then the only thing which has changed is instead of having things in the vertical direction, so now this is no lobe in x direction, so no variation in x. That's what that 0 means. And 1 basically means variation, one lobe variation in y. So basically, the whole field has has tilted by 90 degrees. So instead of now the field is pointing in the field is pointing parallel upwards. So this is EY field, and what I have here is an HX field. Sorry, it'll be yeah. So the field has is pointing upwards like that. Thus, the field has to be 0 in the top and the bottom. So it's an EY field and an HX field. But the field has basically tilted on the two sides. Because there is no symmetry in this waveguide, because A is not equal to B in general case, the propagation constant of this field is going to be different than the propagation constant of the previous field we have over here. The velocity with which these two fields are traveling are going to be different. They are two independent eigen solutions of my Helmholtz wave equation. So they are, if I took this, and again remember your eigen solutions are also orthogonal solutions. Uh, Orthogonal meaning that if I took the overlap integral between the two solutions, those would always be 0. So energy from one solution can never go to energy from the other solution if the waveguide does not change. So once the mode is excited, that's how it's just going to take that its energy and it's going to propagate with its own velocity, with its own distribution, and not interact with any other mode around it. But that's how the TE01 mode looks like. In this case, this waveguide was not single mode as I had plotted it. So let's look at what a TE11 mode would look like. Uh, Again, 1-1 tells you one lobe, one peak in X, and one peak in Y. So there is going to be a variation in X direction and a variation in Y direction too. So the way it would look like is a field variation where again remember in this case TE11, because there is one peak in x and one peak in y in terms of the cos and the sine functions, you would now notice that you have both Ex component, you have both uh, you have an Ex component, come on, Ex and Ey component present. And similarly, you will have Hx and Hy component. What is plotted here is the sum of these two components. Ex varies. Ex, which is in this direction, would have a, a, a sine function in x direction and a cos function in y, and Ey would have a sine function in y direction and a cos function in x. So when you vectorially sum these two components, these are the resulting fields you get. So now you notice one thing, as opposed to your either TE10 mode or a TE01 mode. In TE10 mode, the only H field which is present, which is the main H field which is present, is over here on the top, and this intensity is much weaker. So the current which is generated on the top is going to be larger in density compared to the current which is generated on the side walls. When you go to a higher order mode, like a TE11 mode, now you notice more energy has been pulled towards the outside of the walls. So if you note, you see that you start creating hotspots, hotspots meaning large intensity variations over there. You start creating larger hotspots on the side of the walls. It's telling you that in this case, when it is TE10 mode, most of the energy is traveling in the center of the waveguide where you have air, and by the time you hit the outside walls, the Poynting vector will go to zero. The energy, electromagnetic energy, will go to zero. As you go to higher modes, the energy is being pulled towards the sides, towards the edges of the waveguides. It's not going through the center. Part of the energy is getting pulled towards the sides, and it's not going to be a simple monotonic function. If you look at the energy distribution, you're going to have peaks and troughs in different parts. In fact, the zero energy is going to be carried somewhere here. Somewhere here in the center, there's not going to be much energy being carried, because the electric field over there is going to be zero. In that range, or even in the center, the electric field is zero. So the energy is, instead of traveling through the center, now the energy is traveling closer to the walls of the uh, waveguide. And if the conductors are not perfect conductors, then the loss should increase quite appreciably. So the loss for the higher order modes is expected to be much larger as compared to the loss for the lower order mode. The lower order mode energy is mainly traveling in the center where there is air. As you go to higher order modes, the energy is being pulled towards the sides of the waveguides. This is also true for the TM mode. This is the TM11. Again, remember, TM01 or TM10 do not exist. So, uh, this is again the field distributions you're going to get in the TM mode. Uh, and the difference, the electric field variation, if you notice in the TM mode, TM11 mode is very similar to TE11, at least in its distribution, except uh, it has switched by 90 degrees. So you have larger electric field over here versus on this side. But if you look at the distributions inside, it's very similar to the TE11 mode. except things have shifted by 90 degrees. However, if you notice the magnetic field distribution is basically has zero in the center, and it has a so it basically is one trough, one zero kind of a field, whereas the magnetic field in a TEM mode is different distribution than the magnetic field in a TE distribution. So again, energy is traveling closer to the side of the walls, and in fact, most of the energy is traveling closer to the side of the walls, and thus you're going to get very high losses for TM modes as compared to the TE modes. These are the distributions. What I've plotted is this is basically whenever you're doing any designing the waveguides, you do these kind of simulations, and then you look for these plots. Uh, uh, by looking at the plots, you get a lot of the story without having to do complex maths through them. So these kind of pictures become really important for understanding physically what is happening within these waveguides. Are there any questions on these? Any questions?
No, so they don't have any question.
All right. Let's then continue further, add more concepts. I'm just going to go to a new PowerPoint slide. Uh, I'm just using what we had done yesterday, and we'll continue further on that. And let me just go back to my tablet. All right. So we have seen mathematically that uh, TEM mode does not exist. We have seen mathematically that when I go to TEM mode, when I try to look at, let's say, we know that TE 10 exists, but TE 00 does not. There's no field present when TE 00. And similarly, TM 01 or TM 10 do not exist. And if TM1001 does not exist, TM00 will not also exist. So we have seen mathematically that EEM modes are not supported in this waveguide. In a rectangular waveguide. When we did the maths, the solutions mathematically pointed us to the fact that these modes do not happen. So let's try to understand physically why this happens. Like, what is the physical reasoning behind it? Why, like, mathematics is all fine and dandy, but I'm a big fan of Richard Feynman, who said that if you cannot explain things physically to a second year student, then you don't understand it. So we should try to figure out why are TEM modes not going to be supported in a rectangular waveguide. Remember, TEM modes are supported for your coax cable. For a coaxial cable, the TEM modes are supported within that cable. Uh, so to understand this, let's look at the geometry. We have said that we have a rectangular waveguide, and for TEM mode, HZ should be 0 and EZ should be 0. If HZ is 0, that means only HX and HY components can exist. Only these two components exist within my magnetic field distributions. Only these two components exist. No other component exists around that. And we also know from the equation, from the Maxwell's equation, del dot B has to be equal to 0, which basically is the fact that the magnetic field lines, H lines, have to close on themselves, have to loop on themselves. That's your one of the basic postulates of electromagnetism, that the magnetic field lines have to turn around and close on themselves. In TE modes, they're closing on themselves by going out and creating a current, and the current is flowing around and coming back into the structure. So now what happens here is that if TEM mode was existing, then HZ does not exist, so this magnetic field lines cannot loop around the Z plane, which is what we had seen yesterday when we were doing the TE modes. When we were doing the TE modes, we had seen that the H plane was, the H field was looping in a Z direction. So, but if HZ does not exist, then, and the magnetic field has to loop on itself, then the solution has to be such that it has to loop in the transverse plane. Because of this, because HZ is 0, the field lines, H field lines, have to loop in transverse plane. There's no other option I have available. They can't loop in the Z plane, so they have to loop in the transverse plane, in the XY plane. This being X and this being Y. Now comes the other problem. The other problem is, well, if I have a loop line that tells me that H dot dl, this is your Ampere's law, this has to be given as the current I, or mu naught I. So you get into the problem now that because these lines are converging on themselves, this equation tells you there must be an enclosed current. That there should be an enclosed current. That's Ampere's law. Both these laws are universal laws. Both these laws are fundamentals of nature. They cannot be broken. So The only thing which can happen is the waveguide is going to say, well, I cannot satisfy both these laws together, so I will not allow you to go through. I will not allow the solution to go through. I will TEM modes cannot exist. So TEM modes cannot exist in waveguides with no inner conductor. Anytime you have a waveguide where you don't have any inner conductor, you will not get a TEM mode. If you look at your coax cable, this was the transmission line analogy you had done before. You had done it probably with circuit theory, but in reality, in uh, transmission line, you have an inner conductor carrying current in one direction, and you have an outer conductor carrying current in the other direction. What do you get? You effectively get an electric field which is pointing from the inner conductor to the outer conductor, depending on where it is in Z. It could be up or down direction. And then because of this inner conductor, you have magnetic field lines which are looping around the conductor. So you have magnetic field lines looping around the inner conductor. And now you notice, well, it's not an XY plane, but the E is perpendicular to H, and both are perpendicular to Z, the direction of propagation. So you took this transmission line and you analyzed it with an equivalent circuit model. You basically said, hey, I have an electric field confined within the two conductors that acts like a capacitance per unit length. And I have a magnetic field looping around between two conductors, and that's as if I have an inductance per unit length. So basically, we can. So basically, you defined. So basically, you defined a circuit model which was an LC circuit, which was coupled oscillators, and thus you came up with a wave equation. In reality, if you actually go and calculate the fields inside, what you would get in these coax cable is a TEM mode. That is virtually the only practical waveguide where you have a TEM mode. Almost every other waveguide do not have TEM modes, would have either TE or TM modes. And uh, many times, uh, they may not even be pure TE or TM. If you go to dielectric waveguides, it's what we call quasi TE or quasi TM modes. The in quasi TE, the EZ component exists, but it's a very, very small component, so we can neglect it for all practical purposes. So again, remember, TEM modes can only exist if there is some kind of an inner conductor present, which allows the magnetic field to loop around in the XY plane or the transverse plane, and allows you to maintain the Ampere's law. Allows you to maintain that if there is a looping current, if there is a looping magnetic field, there must be an equivalent current somewhere else. Any questions on this?
So in venue when we don't have any questions, or we can continue.
All right. And this other room is okay too? Soda is? Okay, then let's continue. Let's look at some of the terms we have not spent so much time on. Let's quickly take a look at the terms like phase velocity. What is propagation constant going to be? Phase velocity. So let's look at properties of the modes. In remember the beta we have already seen before. The propagation constant is going to be given by omega square mu epsilon minus m pi by a square minus n pi by b square. This part here is the propagation constant in the medium. And the other two terms we're getting is the confinement effect, how we have confined the energy and how that changes the propagation term. We had said that the cutoff omega c is when propagation constant is 0, just at the place where the gamma term which we had defined goes from positive to negative, from 0 to from real part to imaginary part. So beta is equal to 0 at that point, and we know omega c is going to be given by 1 by square root of mu epsilon square root of m pi by a square plus n pi by b square. So if I write my beta, I can write it in terms of the equations I have. So if I write my beta just becomes, if I take omega square mu epsilon out, I get omega square root of mu epsilon. I get 1 minus, when I get omega square mu epsilon out, this term just becomes 1 by mu epsilon of the term over here, which is nothing but omega c. So I get omega c by omega square. Again, remember this part is nothing but beta in the medium. It's telling you that the beta of the waveguide has decreased from the medium by how much off you are from the cutoff frequency, how high you are from the cutoff frequency for that specific mode. Again, notice that this equation is exactly the same as in form as in parallel plate waveguide. The only thing which is different is omega c has now the second confinement term. In parallel plate waveguide, the confinement was only happening in one direction, so you only had m pi by a square. Uh, Now the confinement is happening in the other direction too, so you start getting the second term around. Similarly, if I write my Vp, Vp is given by beta by omega, sorry, omega by beta, 2 pi f by lambda, yes. Vp is given by omega by beta, and if we substitute the terms from the previous equation here, if I substitute that term, you get omega by omega square root of mu epsilon 1 minus omega c by omega square. And 1 by mu epsilon, square root of 1 by mu epsilon is nothing but the Vp in the medium, the phase velocity of the electromagnetic field in the medium of of mu and epsilon, divided by omega c by omega square. And again, remember, as we had discussed before, this term is going to be less than 1, so the phase velocity in the waveguide for a mode is going to be greater than the phase velocity in the medium. Does it create any issues? No, because energy is not traveling at phase velocity. Energy is traveling at group velocity. Energy is traveling at that, and that group velocity is given as 1 by d beta by d omega. So we have to take the derivative of beta with respect to omega to get the velocity. You can take the derivative, it's not that difficult to do. But normally we do it in a slightly better way. Our dispersion relationship is basically the relation between beta and the properties, the frequency and the properties of the term minus m pi by a square minus n pi by b square. If I take this equation and I take a derivative with respect to omega, then you will get 2 beta d omega as 2 omega mu epsilon, and these are nothing but constants. These two terms here are constants. So when I take a derivative with respect to omega, those go to 0. So all that is basically left. What I'm looking for is d beta by d omega. So I get d beta by d omega as omega mu epsilon by beta. So we can now calculate the group velocity. So group velocity Vg is 1 by d beta by d omega, and is basically when I substitute the previous term, I would get beta by omega mu epsilon. But omega by beta is phase velocity, so V group is 1 by phase velocity, 1 by square root of mu epsilon square, which is nothing but the phase velocity in the medium. So it's telling you V group times V phase is going to be given by V phase in the medium. This is the very same relationship we had seen before for parallel plate waveguide also. So we get exactly same what we had seen before. V phase is going to be given by your V phase medium divided by 1 minus cutoff frequency by the operating frequency square, and a V group is going to be given by V phase medium multiplied by 1 minus Fc by F square. So there is similar relationship we have gotten here, but in deriving this relationship, we assumed that mu and epsilon did not change.
So excuse me, sir.
Yes. Yes.
And the previous slide we have one doubt, sir.
Okay, sure. All right.
Should be V medium whole square or V group velocity into phase velocity is equal to should be velocity of the medium
Square. Yes,
whole
V
square.
square. You're right. Should be V medium square. Yes. Thank you.
Thank you, sir.
Yeah, that's why I put that. Yeah, thank you very much. So in deriving this relationship, we had assumed that mu and epsilon did not change with frequency. Which is true if the medium is air. And for many waveguides, that is perfectly true. The waveguides are very hollow. So if the medium is air, this is true. This is, oops. However, if you put some other material in, for high frequency waveguides, normally you tend to put Teflon in sometimes. If you put other materials in, then if mu epsilon has frequency variation, mu epsilon has a frequency variation, then Vp and Vg will not be equal to Vp medium square. And that relationship is not true any further. If we take a look at the dispersion relationship, beta square omega square mu epsilon minus m pi by a square minus n pi by b square. What you notice here is that uh, if these terms were not present, if it was just beta medium, then if mu epsilon is not changing, if again the condition is same, if mu and epsilon are not varying, then what would happen to your waveguide V phase, and this would be only the case of the medium, would be given by omega by beta, would be, as we've said, omega by omega square root of mu epsilon, if that terms did not exist. And now you have 1 by square root of mu epsilon. V phase medium will not change with frequency. If I go to different frequency, the will not change with frequency. But now for waveguides, your beta square, beta is omega square root of mu epsilon 1 minus omega c by omega square the square root. As you're going to higher and higher frequency, this term is decreasing. So the value of beta is increasing with frequency. As omega increases, value of beta will increase and will approach that of the medium. If I go to omega, which is much, much larger than the cutoff frequency, I basically only have my beta just approaches the value of omega square root of mu epsilon, which is the beta of the medium. So now you see that beta is varying with frequency, and if I calculate Vp or Vg, these will vary with frequency too. Vg, which is really what we are mostly concerned with, how the energy is traveling, is going to be Vp medium square root of 1 minus omega c by omega square. So as a frequency is increasing, the group velocity is also going to increase. So it's telling you different frequency components are going to travel through the waveguide at different speeds. This is dispersion. And because the dispersion is coming, why are this dispersion coming from? Dispersion is coming from due to the existence of these terms. If these terms were not present, there would have been no dispersion. V phase and V group would not have changed with frequency. Because the dispersion is coming due to the terms we have here, and these terms are coming due to waveguide confinement, this specific dispersion is called waveguide dispersion. This is change in velocity change in Vg with frequency due to mode confinement. This plays an important role. Remember, when you are sending information, you're going to be sending pulses through. You're not just going to be sending, you're going to be sending ones and zeros, or you're going to be sending some amplitude. So you are going to be sending some pulses through. The wave is just the horse. On top of the horse, you're going to add some information. And your Fourier tells you that when you have some time variation, if I'm turning this wave on and off, let's say I want to send ones and zeros, I'm turning this wave on and off, then because there is a variation in time, the signal would have multiple frequency components. And what would happen to these frequency components as they travel through the waveguide? They will travel at different speeds, and because they'll travel at different speeds, they'll start to disperse. So I would not get the exact same information back. The faster I modulate the wave, the smaller the time component is, the larger the frequency component is going to be, so larger the dispersion is going to be within the waveguide. And because this dispersion is coming from the confinement factor, from the fact that we took a wave and we put it inside a waveguide and we forced it to go to zeros at the boundaries, this dispersion is called waveguide dispersion. Any questions on this? All right, let's take a look at waveguide impedance or wave impedance. For the TM mode, you will notice TM mode again, wave impedance is related to the two perpendicular fields, electric field divided the magnetic field, the perpendicular components in the transverse direction. And you notice that this wave impedance could be, again, remember for TM mode, you have uh, EX present, you have EY present, you have HY present, and you have HX present. This forms one pair carrying wave power. This forms another pair carrying wave power. So if you notice eta Tm and you do this calculation Ex by Hy, or you do the calculation of minus Ey by Hx, looking at the field components we had before, you get exactly the same value. So Ex and Hy are related by the same term as Ey and Hx are. And this is expected because one, the material is the same, and second, the confinement mode, the confinement factors are effectively the same too. So the impedance in the TM, if you just substitute the values of these fields, will be given by square root of mu by epsilon multiplied by 1 minus omega c by omega square. And this is nothing but eta of the medium multiplied by 1 minus omega c by omega square. Eta t is much easy to think about. Eta t, there are only two fields present. So you have a field of Ex and a field of Hy. And when you substitute these, the answer you'll get is square root of mu by epsilon divided by 1 minus omega c by omega square. Both these terms are very similar to what we got for parallel plate waveguides, except the only difference is omega c term. When you're calculating the cutoff frequency for the mode, that is at slightly that has another term in it, n pi by b term in it too. Any questions? All right. Let's look at the attenuation terms. And again, I'll probably bore you for some time, but bear with me. And we'll look at the final terms later on, what it looks like. Again, we are assuming that the resistance of the metal boundaries of the metal conductors is very low, and thus the electric field distributions or the magnetic field distributions we have calculated assuming that the resistance was zero or the conductance was infinity, that distribution doesn't change too much. So the idea is we have this waveguide, and because of this waveguide, we know that we have some current which starts to flow on the top for different modes. Because of this current flowing, and if assuming that the resistance is small, we are assuming that this current distribution doesn't really change. So we should be able to calculate the answer. So let's look at TE mode, and let's look at effectively your TE10 mode. It's difficult to do analytical expressions for more modes than 10 because you start getting a lot of terms through. But let's just understand TE modes. And again, we said that we are going to calculate alpha by calculating the total power going through and how much power is being absorbed by my absorbed in the resistance. So the average power traveling through propagating will be given by P going in Z direction, integral of the the Poynting vector, half of E cross H star. We said that we have electric field in one direction, X direction, and magnetic field in Y direction. So it would be integral over the whole waveguide 0 to A, integral from 0 to B, half of, basically I'm just doing the component, half of E X H Y star in magnitude, the complex conjugate, dx dy. Substituting the terms we had derived before, just substituting, putting all the terms in and doing the calculations, you basically get a sine square variation from 0 to a, sine square pi by a x kind of variation, which is nothing but when you integrate is a by 2. So it's a simple integral to do. You get the answer that this is going to be equal to omega mu beta AB times a h naught square by 4 pi square. This is the average power propagating in the mode. Then we need to calculate the loss. and the power loss due to the resistance is going to be twice the power lost on the bottom plate where y is equal to 0 plus twice the power loss. Whatever is the current flowing in the bottom plate is the same current flowing in the top plate. So it's going to be twice the power lost at y is equal to 0 plus twice the power lost at x is equal to 0 term. And each term, power loss at x is equal to 0 is going to be given by the integral of the current half Js at x is equal to 0 square times the resistance, integrated it over the complete uh, complete plate. So at x is equal to 0, we have a plate so at x is equal to 0, we have current flowing in this plane over here. So I have to integrate this current going over this whole region. So I have to integrate it in y direction and I have to integrate it in z direction. So to integrate it over a plate, it will be dy dz, and the integral of z, we're saying let's measure the power going through 1 meter, power lost through 1 meter. So this would be z from 0 to 1, whereas y would be from 0 to b. We had already calculated Js yesterday, and if you put the term in, you get b by 2 from yesterday's term. It's a very simple integral. This term is nothing but a constant. The current we know is flowing constantly in that region. So it will be b by 2 h naught square by multiplied by the resistance we have for this case. Similarly, we can calculate PL at y is equal to 0, and there you're going to have two terms. There is going to be a term, so y is equal to 0 is basically looking at taking that waveguide and now looking at how the current is flowing in this plate, and we know that the current flowing in this plate had a component in x direction and a component in y direction. So basically this was going to be two terms there. We would integrate it. Obviously we are integrating z from 0 to 1. Zero to 1 meters, and we integrate x, the two terms we have present, one term coming from the hz component, the current coming due to hz component flowing in the y direction, and the other current coming due to the electric field in magnetic field in y direction, magnetic field in x direction parallel to that same structure. So you're going to get terms which are going to be half of Js at y is equal to 0 square integrated from 0 to a over this plate, thickness of that plate, plus you have half of Js due to your, so this is due to the x component of the field. This is due to the z component of the field at y is equal to 0 square in dx direction. And when we substitute again these terms, we had calculated it yesterday. When you substitute, this loss is going to be a by 4, 1 plus beta a by pi square, h dot square by r s. So the total loss which I see is the sum of those two losses, and after just doing some simple algebraic manipulations, it turns out to be b plus a by 2 f by fc square h dot square times rs. And the alpha, just using the same ones we had seen before, alpha c with respect to te is going to be given by 1 by beta b square root of pi f mu c, sigma c the conductor value, 1 minus fc by f square multiplied by 1 plus 2b by a fc by f square, or you can also write it in terms of the resistance, would be equal to rs 1 plus 2b by a fc by f square divided by beta b square root of 1 minus fc by f square. That is the loss due to the TE mode. And one thing you would notice is that as a B increases, the loss will decrease. As the value of B increases, normally you are operating at a much higher value than the cutoff frequency, because at cutoff frequency the loss is going to be very, very large. So you're operating few times higher than the cutoff frequency. So this term is small. So if I was looking at the geometry, as I increase the value of B, my loss is decreasing. And then the other term which you notice is again that this is not now like your parallel plate waveguide. In parallel plate waveguide for TE term, if you plot this equation, in parallel plate waveguide, for TE, as the frequency increases above the cutoff frequency, the more you increase the frequency, the lower the loss would become. It would monotonically decrease. In this specific case, that is not going to happen. As the frequency is increased, as this frequency keeps on increasing, the loss would drop sharply before going to a minima, and then yes, you have a term over here, but you also have a term. You have a term over here, and you have a term over here. Uh, as the frequency keeps on increasing, this, and then you have a term over here too. So these two terms would decrease with frequency. The term over here is decreasing with frequency. The term over here is decreasing with frequency. But then you have a square root of f term showing up, which increases with frequency. So after some time, when f has become much greater than fc, the effect of these two terms become negligible. And then it tells you that the loss is going to increase nearly as the square root of frequency. So loss is going to start to increase again. It's going to be a different behavior than the parallel plate waveguide. Let me just add some slides. Any questions?
Sir,
Yes.
so you told that the TEM mode exists only when there is an inner conductor, sir.
TEM, yes.
TEM. So why are we not having inner conductors for rectangular or square waveguides?
Or the loss is so much higher at these frequencies. Because the inner conductor is going to add loss too. So if I add the inner conductor in, the loss just becomes just too much. Again, remember in this specific case, in rectangular waveguides, especially for the TE10 mode or TE01 mode, depending on whether A is greater than B, what you have is the wave is traveling really in the air inside, and it's only the ends of the wave which are interacting with the conductor. That's how the loss can be reduced. With an inner conductor, you have a huge current density on the inner conductor, and as you go to higher and higher frequencies, those inner conductors starts to create a huge loss. So yeah, when you're working at gigahertz or even a few gigahertz, coaxial cable with the inner conductor works well. However, if I'm now operating at few tens of gigahertz, um, the loss of that coaxial cable would be just too much for me to bear.
Thank you, sir.
Right, so any other questions? Or so if I was going to plot this, now there are two competing factors happening with me. One, we notice alpha TE will first decrease with frequency and then increase. And alpha TE decreases as value of B increases. as A by B ratio decreases. So now we have a compromise we have to make. Remember, what does A by B ratio does? A by B ratio, and again we are assuming A is greater than B. Come on, stupid. We are assuming A is greater than B. So we know we are going to have a cutoff frequency FC 10 here. And then after some time, we are going to have another cutoff frequency, which is FC01. If A by B ratio decreases, if B is approaching A, then that cutoff frequency is approaching the value of the first mode. If B keeps on increasing, if I want to reduce the loss, B keeps on increasing, this cutoff frequency will now start to move closer and closer to FC01. And again, remember, it is this region which is single mode. So as B increases with respect to A, the bandwidth of single mode operation decreases. The frequencies at which the single mode only a single mode would be present, and most of the times we want that single mode, the frequencies over which the single mode would be present, that bandwidth of single mode would keep on decreasing. So we have two competing factors. One factor is how much bandwidth do we want, over what frequencies do we want this waveguide to still operate at, and the other is the loss. A typical practical solution is that typically the compromise which is made is that B is approximately half of A. Which is a compromise made with respect to how much bandwidth I get versus how much loss I get within the waveguide. So I'm going to plot this in now conditions. You have your cutoff frequency FC 10. As we are going from the cutoff frequency, as we are going higher and higher above the cutoff frequency, below in this region here, only the evanescent wave exists. No propagation. Whereas over here, when Fc is equal to F is going to the operating frequency is going to be Fc, the term which we have goes to 0. 1 minus Fc by F term goes to 0. So the loss is going to be infinity. And that term is going to dominate as I change F close to it. So the loss is going to drop down very, very quickly. So you're going to see some behavior like that. Loss is going to drop down very, very quickly. And roughly at twice Fc by 10, roughly around that region, it's going to achieve the minimum loss. Roughly around that point. After that, the loss is going to start increasing again. This variation over here, when we go to larger and larger frequencies, this loss is going to be proportional to square root of f. That is your TE10 mode. So the loss is going to drop very, very quickly, approximately at twice the cutoff frequency. You're going to get the minimum loss. And typically for the waveguides we design, this loss is actually very, very low. This loss is of the order of, the minimum loss is normally of the order of 0.1 dB per centimeter. To put this in perspective, per meter, 0.1 dB is roughly 5% of the power lost. So if you travel over 1 meter of the waveguide, you would lose about roughly, 0.1 dB roughly 5% of the power. Roughly 5% of the power would be lost over over 1 meter. Similarly, if we calculate the loss for Tm, alpha C for Tm, all you have to do is do the same maths we did for Te, and I'll put this maths online for you guys to do it at home. This is going to be 2 Rs B by A square plus A by B square divided by eta AB square root of 1 minus Fc by F square and 1 by A square plus 1 by B square. The Tm mode is going to be probably going to be much higher than the Te mode. The cutoff frequency of the Tm mode is going to be somewhere here, 1, 1. And the loss of the Tm mode is going to be higher. Obviously, it's going to be infinity, and it's going to have a similar fashion, but it doesn't go down as sharply because of these terms over here. Doesn't go down as sharply as the Te mode does. It has a more of a roll-off factor. And I'll give you a question to calculate these terms for practical waveguides, and then it is going to increase again. So this is the loss for Tm11 mode. It's going to have, this one is going to have a sharper drop. This one is going to have a more roll-off drop, and then it's going to increase again. This loss is approximately 3 times larger than Te loss. Approximately, for practical waveguides, it's approximately 3 times larger for these cases. So it's very clear why we like to use TE10 mode. It's a mode which has the lowest cutoff frequency. We can make a waveguide which is a single mode using that mode, and it is the mode which has the lowest loss with respect to frequency. So everything works out for this mode from practical purposes. And I'll stop here for today. If you have any questions, let's try to answer those. Tomorrow, there are a couple of things left, but no maths. We have looked at the solution. We have looked at these solutions. These solutions exist, but we haven't still learned how to excite them, how to excite this mode in this waveguide. So I'll briefly describe how those excitations work, and uh, no maths in there, just how things work. Uh, because to do the maths, we need to know antenna theory too, which you probably do in a different course. But I'll show you how modes can be excited, and then we'll do some questions.
Currently, said that what they don't have any question.
Okay. What about the other class?
What is the advantage of using TEM compared to these two modes, especially in coaxial cable?
A coaxial cable, basically the TEM mode has no cutoff frequency. So the coaxial cable will work even if you go to very, very low frequencies, right? You have looked at a coaxial cable. Even if I send 100 hertz of the signal through, the coaxial cable will carry that signal. So TEM mode, as you have seen in the parallel plate waveguide, has no cutoff frequency. It is always supported. So whatever I do, I can send signal through. Whereas rectangular waveguide, if I went below this region over here, if I went for F below the first cutoff frequency, there is no guidance provided. The wave cannot even penetrate through. A good example is when you go through tunnels. Do you have tunnels around your area? I think you have some hills around there, right? And there may be some tunnels, but if you go through tunnels, or if you go, I'm sure there are tunnels on the Malabar coast. If you go through tunnels, next time when you go through a tunnel, turn on the AM radio and then turn on the FM radio. The AM radio, you would lose all your propagation, you would lose all your reception, whereas the FM radio would still work. AM radio is working at very low frequencies. FM radio is working at megahertz. The tunnel is acting like a waveguide. FM radio can penetrate through as a mode. AM cannot. So that's the advantage of using coaxial cables versus waveguides. But then the coaxial cable, because of the inner conductor, the loss in the coaxial cables, and I don't know whether you did transmission lines, you studied the loss there or not. But the loss in the coaxial cable, because of the resistance in the coaxial cable and because of the leakage between the two conductors, the loss actually starts to become very, very high as you increase the frequency. So that coaxial cable becomes very, very lossy at high frequencies as opposed to a rectangular waveguide with air in it. So different applications, right? In fact, the cables you have to build, the cables which are working at 2.4 gigahertz, good cables would always have gold coating on them. And those cables become expensive. Even the connectors there have gold coating. If you have SMA cables in your labs around, you can see that the connectors are gold plated to try to reduce the loss of that cable. That makes those cables very expensive, as opposed to rectangular waveguides, which could be made with copper or brass or even aluminium or even sometimes steel. Uh, People are even making waveguides with plastic and then coating them with metal inside to create the boundary conditions. So, so the loss at high frequencies keep on decreasing. Uh, Now, compared to this, when you go to even higher frequencies, if you go to terahertz, which is 10 to power 12 hertz, where there's a lot of research happening right now. If you go to terahertz, even these rectangular waveguides fail. They have too high loss. Again, remember TE loss is increasing as square root of f. So if I go from 10 gigahertz to 1000 gigahertz, my loss has increased by a factor of 10. So that loss becomes prohibitive when I go to higher frequencies of even at terahertz. These rectangular waveguides start to become a problem. So people are started to use dielectric waveguides there now. If you go to optics, which is now 500 terahertz, or anywhere, like if you're doing optical communication, that's 193 terahertz. The metal is very lossy there. And you have seen that yourselves. If you try to pass light through metal, there's hardly any light going through, right? So you know that metals are have heavy loss in the optics. Even these rectangular waveguides completely fail there. There's nobody even tries to do any rectangular waveguides in optics domain. You go with dielectric waveguides over there. So different applications require different solutions at the end, right? Coax cables are very low cost cables. The TEM mode has no cutoff frequency, so they can operate from 0 hertz to wherever the loss becomes prohibitive. When their loss becomes prohibitive, then you have to go to a rectangular or a hollow waveguide. And when the hollow waveguide loss becomes even prohibitive, then you have to go to non-metallic waveguides where the current is not even generated. Does that answer your question? Does it answer your question or no?
Yes, sir. Yes, sir.
Okay. Any other questions?
No, sir. No questions.
All right. Then I'll see you tomorrow morning.
Yes, sir.
Yes, sir.
All right. And I'll send you some questions by tomorrow. So before you come to class, you'll probably have some list of questions.
Okay, sir.
All right.
I'll
Thank you.
send it.
Have a nice day. Bye.
Thank you, sir.
All right.